Welcome back, design junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. Imagine an environment so violently pressurized that solid steel flattens like a rubber ball.
Yeah, and liquid oil instantly flashes into a solid sheet of glass.
Right. And materials literally shrink when you blast them with heat. I mean, it sounds like a sci-fi movie, right?
It really does, but that is the microscopic reality happening inside the transmission of your car right now.
It's just wild to think about. Today, we are taking a deep dive into the extreme, invisible battlegrounds of modern machinery. We really want to understand how mechanical engineering overcomes three incredibly destructive forces.
Right, which are metal-to-metal friction, high-pressure fluid leaks, and, fatal vibrations.
Exactly. So our mission for you today is to basically decode the hidden physics that keep the modern world turning.
Because it is a fascinating microscopic world to explore. A machine's lifespan is entirely dictated by these unseen micro-interactions.
Yeah, it's all happening on a scale we can't even see.
At its core, mechanical longevity really just comes down to how we cushion moving parts, how we seal those parts to keep pressurized fluids where they belong, and how we isolate the entire system from just shaking itself to pieces.
Because if any one of those three pillars fails...
the entire machine fails catastrophically. There's no coming back from it.
Okay, let's unpack this. Before a machine can shake itself apart, it obviously has to move.
Right.
And separating moving metal brings us to tribology, which is the science of friction and lubrication. Now, when most of us think about oil keeping metal parts separated, we picture hydrodynamic lubrication.
Which is a great starting point, yeah.
The easiest way for you to visualize this is like a car tire hydroplaning on a wet road.
That's a perfect analogy.
When you have conformal surfaces, meaning shapes that naturally hug each other, like a round shaft rotating inside a matching cylindrical sleeve, they basically sweep the oil up into a liquid wedge.
Right, and that wedge physically lifts the shaft and pushes the metals apart.
But if we look at rolling element ball bearings, that logic seems to completely fall apart.
How so?
Well, the contact area between a perfectly spherical steel ball and a flat steel race is theoretically just a microscopic point, right?
On the purely geometric level, yes.
And since pressure is force divided by area, and the area is practically zero, the pressure should be astronomical. Wouldn't that immense force just, squish the oil right out of the way?
What's fascinating here is that common sense tells us, yes, the liquid oil should immediately squeeze out of that microscopic gap.
Right.
But it does not. The mechanism saving every ball bearing in the world is called elastohydrodynamic lubrication, or EHL.
EHL, okay.
Yeah, and in hard EHL, which applies to metals, we're dealing with contact pressures that exceed 700 meganewtons per square meter.
Wait, 700 meganewtons? That is a massive amount of force.
It's basically incomprehensible. But at those extreme pressures, two incredible physical transformations happen simultaneously to save the machine.
Okay, I'm listening.
First, the immense pressure actually forces the steel to elastically deform. The spherical ball temporarily flattens out to create a microscopic flat spot.
Oh, wow. So it artificially enlarges the contact area so the load can be distributed.
Exactly. So the forged steel literally yields to the pressure, acting somewhat like a highly pressurized rubber ball pressing against a hard floor.
It flattens, rolls, and then springs back to a sphere once it's out of the contact zone.
Yes, it is entirely elastic.
Yeah.
But the second transformation is even stranger, and it happens to the oil itself.
Strange how?
Well, liquids are generally considered incompressible, right? But at 700 meganewtons per square meter, the actual molecules of the oil are shoved so tightly together that the free volume between them just vanishes.
Wait, so the oil stops being a liquid?
Because of a property known as the pressure viscosity coefficient, the oil's viscosity spikes exponentially. For a fraction of a millisecond, the liquid oil acts like a solid pane of glass.
No way.
Yeah, it becomes so viscous, so rigid, that it forms a solid wedge, entirely preventing the metal-to-metal contact.
That fundamentally changes how you have to design the system mathematically, doesn't it? I imagine the film thickness calculations for a standard liquid wedge versus a, solid glass wedge must look very different.
They do, and you can see the physics reflected right in the formulas. Conceptually, in traditional hydrodynamic lubrication, if you increase the load on the shaft, the fluid film thickness is significantly reduced.
Because you just physically squeeze the liquid out.
Exactly. But in EHL, the minimum film thickness is only slightly affected by the load.
Really? Just slightly?
Yeah, in fact, the load exponent in the EHL equation is roughly 7 times smaller than it is for hydrodynamic lubrication. The oil film resists being squeezed out because the harder you push on it, the more solid it becomes.
That is just incredible. But there has to be a limit to that magic, right? Like what happens if the machine is just starting up and the speeds are too low to sweep that oil into the contact zone?
That's a very real problem.
Or what if a sudden shock load pushes the pressure past what the glass state can handle? I mean, the fluid film has to break eventually.
It does break, and that puts the machine into the boundary lubrication regime.
Which sounds bad.
It is. When the fluid film is fully penetrated, the microscopic hills and valleys on the metal surfaces, which we call asperities, actually collide.
Because even highly polished metal isn't perfectly smooth.
Right. If you looked at a highly polished ball bearing under an electron microscope, it wouldn't look smooth at all. It would look like a jagged mountain range.
Oh, man. So when those asperity mountains crash into each other under heavy load...
They literally micro-weld together and immediately tear apart. That causes massive friction and rapid wear.
And to survive that, engineers lace the oil with extreme pressure, or EP additives, right? I was looking into these.
Yeah, what did you find?
They contain these active organic compounds loaded with chlorine, sulfur, or phosphorus.
Got on.
And when those metal mountains crash and heat up from the friction, those chemical additives react with the bare iron. They form a metallic salt layer like iron chloride or iron sulfide that is incredibly soft.
Exactly. It has a very low shear strength.
So instead of the steel mountains welding and tearing, this sacrificial chemical layer simply shears away, completely protecting the steel underneath.
It's brilliant. It is a perfect example of chemistry solving a mechanical problem.
It's wild to think about a massive industrial gearbox surviving only because of a chemical reaction happening at a scale of just a few molecules thick.
There really is.
But creating the 700 meganewton glass oil is really only half the battle. Now you have a highly pressurized fluid trying to escape the casing.
Right, which brings us to sealing.
Yeah, how do we keep that fluid trapped inside the machine? That requires static and dynamic seals. And the most universal one you see in everything from plumbing to space shuttles is the O-ring.
The classic O-ring.
Now, to the naked eye, an O-ring looks exactly like a thick rubber band. And basic physics tells us that heat makes things expand.
Usually, yes.
So I would assume that if you have an O-ring sealing a hot spinning shaft, the heat makes the rubber swell up, causing it to seal even tighter inside its groove.
That is a very logical assumption, but it leads directly to one of the most counterintuitive and dangerous phenomena in engineering.
Wait, really?
Yeah, it's called the Gauge-Joule effect.
The Gauge-Joule effect.
Right. When you take a rubber O-ring and stretch it under tension around a rotating shaft, the friction between the rubber and the spinning metal generates heat. But stretched rubber has a bizarre thermodynamic property.
Okay.
It actually contracts when heated. It exhibits a negative expansion coefficient.
Wait, it shrinks. Why would heating a material make it smaller?
You have to look at rubber not as a solid block, but as a microscopic bowl of long, tangled spaghetti noodles.
Okay, I'm picturing spaghetti.
Those noodles are polymer chains. When you stretch the O-ring around the shaft, you're pulling those tangled chains straight and aligning them.
Makes sense.
But when friction adds thermal energy to the system, those aligned molecules get highly energized.
Yeah.
They start vibrating violently, and they naturally want to coil back up into their chaotic, tangled state.
Ah, and because they are coiling up, the material physically shortens.
Exactly.
Oh, that creates a terrifying positive feedback loop. If the heat causes the stretched rubber to contract, that contraction forces the rubber to grip the shaft even tighter.
Yeah.
Which means gripping it tighter increases the friction, which dumps even more heat into the rubber, causing more violent coiling and more contraction. That is a runaway thermal cascade.
Precisely. It happens incredibly fast, and it leads to catastrophic seal failure. The O-ring literally burns itself to a crisp and just shreds.
So how do you engineer around a fundamental material property like that?
The solution is purely geometric. You just never stretch the O-ring over the shaft in a rotary application.
You just don't do it.
Right, you avoid putting it in tension entirely. Instead, you intentionally oversize the O-ring slightly, so its inner diameter is larger than the shaft, and then you compress it circumferentially into the outer housing groove.
So by pre-compressing the rubber, the internal compressive stresses oppose that thermal contraction.
Exactly. The tangled polymer chains are already squished, so adding heat doesn't cause them to shrink and grip the shaft.
It is all about preload. For a static joint, you might compress the seal up to 30% of its thickness and maybe 16% for a dynamic rotary seal.
That's the standard, yeah.
But even with perfect geometry, rubber is still flexible. If the system pressure gets high enough, doesn't the rubber just act like an ultra-thick liquid?
It can, yes.
Like it would just flow toward the lower pressure side of the groove until it eventually extrudes right into the tiny metal clearance between the casing and the shaft, and then it would just get completely sheared off.
That is exactly the failure mode for high-pressure extrusion.
Mm.
The sheer strength of the elastomer is simply overcome by the fluid pressure.
So what do you do in truly extreme environments, like high-speed aerospace turbines where temperatures and speeds would destroy rubber instantly?
In those cases, we have to abandon contact seals entirely. Instead, we use non-contact clearance seals.
Like labyrinth seals. I've seen diagrams of these.
Yeah.
They look like a series of sharp, circular metal teeth that sit incredibly close to the spinning shaft. They don't touch the shaft, but they create this tortuous maze-like path for the fluid.
Right, forcing it to rapidly accelerate and decelerate through those teeth, which continuously drops the fluid pressure.
Yes. But they have a flaw, don't they?
They do. Labyrinth seals are the historic standard for jet engines and gas turbines, but they have a fatal flaw. Because they are clearance seals, their entire function relies on maintaining a microscopic gap between the teeth and the shaft.
Right.
If the turbine shaft vibrates or goes through a heavy transient excursion, say the pilot pulls a high-G maneuver, the heavy shaft crashes into the metal labyrinth teeth.
Oh, man. So the teeth permanently deform or just wear away completely?
Exactly. Once the maneuver is over and the shaft centers itself again, that tiny gap is now permanently larger, and your leakage rate just skyrockets.
Which means your engine loses efficiency and power, so how do you create a tight clearance seal that can actually survive a shaft crash?
That specific challenge led to the development of brush seals.
Brush seals?
Yeah. If you look at a cross-section of a brush seal, it literally looks like a dense, circular metallic broom facing inward toward the shaft.
A metallic broom.
It uses a densely packed ring of thousands of fine wire bristles, often just a few thousandths of an inch in diameter, angled in the direction of the shaft's rotation.
So when the shaft has an excursion and crashes into the seal, instead of grinding away solid metal teeth, the flexible wire bristles just bend and sweep out of the way.
Got it.
And once the shaft recenters, the metallic bristles spring right back to their original position, perfectly recovering that tight clearance.
Exactly. They vastly outperform labyrinth seals because they can survive severe dynamic loads without permanently degrading the system's efficiency.
That is so smart. But you mentioning those heavy shaft excursions actually brings us to our third invisible enemy, vibration.
Ah, yes. The machine killer.
Right. Even if a machine has the perfect elastohydrodynamic oil film and indestructible brush seals, if its massive moving parts are slightly off-center, the machine will violently shake itself apart.
It's inevitable.
Anyone who has ever overloaded a washing machine with wet towels knows exactly what this feels like. The heavy, wet jeans clump on one side of the drum, throwing the center of gravity off.
And when it spins.
The whole machine starts violently walking across the laundry room.
Exactly.
But let's say I take my car to the auto mechanic. They put my tire on a spindle, find the heavy spot, and statically balance it by clipping a small lead weight to the light side. Shouldn't that completely fix the vibration for any spinning rotor?
It fixes it for a short, disc-like object, such as a car tire. That is called static balancing. It simply ensures the center of gravity aligns perfectly with the rotational axis.
Okay.
But imagine a long, heavy rotor, like the steel crankshaft of a diesel engine. You could perfectly balance it statically. If you set it on resting bearings, it wouldn't roll to a heavy side.
Because it's balanced.
But what if there is a hidden heavy spot on the front left of the crankshaft, and it is perfectly offset by another hidden heavy spot, exactly 180 degrees opposite on the back right of the crankshaft?
Ah, so when it is sitting still, those two heavy spots cancel each other out. The center of gravity is technically right in the middle.
Correct. But once you spin that long rotor at high speed, those two heavy spots are acting on opposite ends of a long moment arm.
Oh, I see where this is going.
They generate massive centrifugal forces in completely opposite directions. The front of the shaft is violently pulled left, while the back is violently pulled right.
This creates a severe twisting force.
Yes, a dynamic imbalance that static balancing completely misses, and it will absolutely destroy the bearings. So, for anything longer than a thin disc, Engineers must balance the rotor both statically and dynamically.
Okay, so let's say we balance the rotor as precisely as humanly possible. There is always going to be some residual microvibration, right?
Always. You can never get it to absolute zero.
Why can't we just isolate the machine? Like, why don't we just stick the whole assembly on super soft rubber pads to absorb the shaking so it never reaches the factory floor?
Because if you choose the wrong rubber pads, you will not absorb the shaking. You will amplify it to the point of structural destruction.
Here's where it gets really interesting.
This brings us to the core concept of transmissibility. To effectively isolate a machine, the forcing frequency, which is the speed the machine is shaking at, must be greater than 1.4 times the natural frequency of the mounting system.
1.414, that's the square root of 2.
Exactly.
So if we map out the machine's vibration on a graph and we draw a flat line representing the floor's normal state, past that 1.414 ratio, the curve actually drops below the flat line, meaning the floor feels less vibration than the machine is actually producing.
Yeah.
We are in the isolation zone.
Yes. But to get to that isolation zone, you have to look at what happens earlier on that graph.
Okay, what happens earlier?
If the forcing frequency of the machine happens to exactly match the natural frequency of those rubber pads, a ratio of exactly 1.0, you hit resonance.
And resonance is bad.
Very bad. At resonance, the mounting pads do not isolate anything. They act as an amplifier, multiplying the input vibration by a metric called the Q factor.
How much of a multiplier are we talking about?
In bonded rubber systems, the Q factor could easily be 10 to 40. In undamped metal structures, it can reach up to 1,000.
Wait, let me make sure I'm visualizing this correctly. If your machine is inherently vibrating by just 1 millimeter, but you put it on a poorly chosen rubber pad and hit resonance, a Q factor of 40 means the machine will suddenly start violently swinging 40 millimeters.
That is exactly what it means. It is a terrifying multiplication of kinetic energy.
But wait, every machine has to start from 0 RPM and accelerate up to its operating speed? That means as it speeds up, it physically has to pass through that 1.0 natural frequency resonance point before it can reach the safe 1.414 isolation zone.
You're absolutely right.
How does the machine survive the startup without swinging 40 millimeters and snapping its bolts?
If we connect this to the bigger picture, that startup phase is exactly why engineers introduce damping into the system, like the shock absorbers on your car.
Oh, to absorb the energy.
Exactly. Damping is designed to bleed off kinetic energy and turn it into heat. We add damping specifically to survive that violent momentary trip through resonance during startup or shutdown.
That makes total sense.
Now, the engineering trade-off here is fascinating. Adding damping actually decreases your isolation efficiency slightly when you're finally up at high operating speeds.
Really?
Yeah, but it is a strictly necessary compromise, ensuring the machine doesn't tear itself off its mounts every time you turn the power on.
It is a delicate balancing act of physics. But to fix these chaotic vibrations, engineers first have to be able to measure them accurately.
Which is incredibly difficult.
Right. Because measuring high-frequency shaking, where the physical movement of the metal might be less than a single wavelength of light, sounds mechanically impossible.
It is impossible if you're trying to measure displacement, which is the actual physical distance the part moves. At high frequencies, displacement shrinks to microscopic levels.
So how do they do it in the past?
Historically, engineers tried to measure this using optical wedges taped to the machine, which relied on the human eye's persistence of vision blurring the lines together.
That sounds very imprecise.
They were terribly inaccurate for tiny, fast movements. The modern breakthrough was shifting from measuring displacement to measuring acceleration.
Because mathematically, even if the distance moved is barely a fraction of a millimeter, if it reverses direction and moves back and forth 10,000 times a second, the acceleration force is absolutely massive.
Precisely. The acceleration voltage rises proportionally to the frequency squared, making accelerometers incredibly sensitive at high frequencies.
That makes them the ideal diagnostic tool for detecting microscopic faults, like a single cracked tooth on a gear, before the whole system fails.
Exactly right.
But how does an accelerometer actually work? I always picture the piezoelectric crystal inside the sensor, usually made of synthetic quartz or barium titanate like a sponge.
A sponge?
Yeah, but instead of being full of water, it is filled with electrical charge.
That is actually the perfect way to visualize the piezoelectric effect. Inside the sensor housing, a small mass rests on top of that crystal sponge.
Okay.
When the machine accelerates upward, the internal mass lags behind due to its own inertia, and it compresses the crystal.
When it accelerates downward,
The mass decompresses the crystal. Every single time that crystal is squeezed or stretched, it literally squeezes out juice electrons.
Oh, wow.
By measuring that tiny fluctuating electrical charge, engineers receive an exact, real-time signature of the machine's acceleration.
But dealing with microscopic electrical charges has to introduce its own set of gremlins, right? I mean, if you are measuring a few squeezed electrons, any external electrical noise could ruin the data. I noticed in the research something called triboelectric noise.
Yes, triboelectric noise is a classic pitfall in vibration measurement.
How does that happen?
Well, the accelerometer sends those squeezed electrons down a long coaxial cable to an external amplifier. That cable has an inner conductor, an insulating dielectric layer, and an outer braided shield.
Right, pretty standard cable.
But if the cable itself is allowed to whip around and vibrate against the machinery, the internal shield of the cable can physically separate from the dielectric layer inside.
Uh-oh.
Yeah? When they part, the friction generates a static charge, dumping a load of excess electrons directly into the conductor.
And the amplifier at the other end has no way to tell the difference between these fake static electrons and the real signal electrons coming from the squeezed crystal.
Not at all. So a loose whipping cable looks exactly like a failing machine on the diagnostic monitor.
You could be tearing down a perfectly good $500,000 turbine just because your sensor cable was wiggling.
Exactly. So you have to tape down the cables securely.
And you also have to ensure these sensors actually work under extreme duress. How do you calibrate a delicate crystal designed to measure catastrophic machinery failure?
You subject it to a highly controlled extreme shock. The industry standard is the drop ball calibrator.
Which is exactly what it sounds like.
Pretty much.
Yeah.
You solidly mount the accelerometer to a massive steel anvil. Then you drop a hardened steel ball onto the anvil from a highly specific height.
Okay.
By changing the padding material on the impact surface using different plastics or metals, you can shape the shock wave, generating clean, repeatable shock pulses up to 15,000 Gs.
15,000 G.
Yeah. It verifies that the sensor can survive and accurately report the exact kind of violent impacts you would see if a gear suddenly shattered.
15,000 Gs. The sheer scale of the forces we are dealing with today is staggering. From the massive 700 meganewton pressure inside an elastohydrodynamic oil film to the microscopic squeeze of a barium titanate crystal.
And that leads to a crucial final thought for you to consider as we wrap up.
Let's hear it.
A machine is not just a collection of distinct parts. It is a deeply interconnected ecosystem. Think about the chain reaction of failure.
Okay.
Let's say a microscopic temperature fluctuation slightly lowers an oil's pressure viscosity coefficient. Because the oil doesn't harden enough, the fluid film breaks, and two metal asperities collide.
Right, the mountains crash.
Exactly.
Yeah.
That localized collision changes the vibration signature of the rotating shaft. That new dynamic vibration loads the rubber O-ring unevenly, which generates localized friction, triggering a gauge-joule thermal contraction.
And suddenly your seal burns up, your fluid leaks out, and the entire system crashes.
Engineering isn't just about understanding one piece in isolation. It's about mastering how all of these invisible physics dance together.
The invisible dance of forces inside the metal. If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.